All right, first thing I wanted to do is go over the FRQ that was due yesterday. So we have this reaction of calcium carbonate solid producing calcium oxide solid plus carbon dioxide. We're told that when it's strongly heated, a 2 mole sample of calcium carbonate is placed in a rigid 1 liter reaction vessel from which all the air has been evacuated. The vessel is heated to 898 degrees Celsius, at which time the pressure of carbon dioxide in the vessel is 1 atmosphere, while some calcium carbonate still remains in the vessel. Calculate the number of moles of carbon dioxide present. All right, so this is, let me shift screens here real quick, a Pivnert question. Okay, we were told the pressure was 1 atmosphere, told the volume was 100 liters. The ideal gas wall constant, of course, is 0.0821 liter atmospheres per mole Kelvin. And we were told the temperature in Celsius, which we had 273 to get 1171 Kelvin. And so that means then that the number of moles turns out to be 1.04 moles. All right. That's part A. That was 1 point. Part B, write the expression for Kp, the equilibrium constant for this reaction, and determine its value at 898 Kelvin. All right, well, that's even easier. Let me shift views yet again. All right, so Kp is just based on the pressure of carbon dioxide. Instead of pressure, if you had said Kp equals concentration of CO2, that would be okay as well. We were told the pressure is 1 atmosphere, so Kp is 1. Done. No calculation needed in this case because we had solids. We don't include the solids. I know some of you were putting ones in for the solids. That's fine. But Kp only depends on carbon dioxide, and carbon dioxide we know is 1 atmosphere. So the Kp is 1. All right. Last part. Experiment was repeated, but this time with a 4 mole sample of calcium carbonate. On the graph, draw a curve showing how the pressure of carbon dioxide would change. Well, what does Kp depend on? Carbon dioxide, right? Does it matter how much calcium carbonate? Let me go back to my other screen. I sounded all weird. Okay, Kp, I don't see calcium carbonate in there. It doesn't matter. And remember, there was calcium carbonate left in the chamber anyway. It wasn't like it all got used up. So it has no effect. So the graph should flatline at 1 atmosphere again, just like it, ooh, man, like it would have been the first case. All right. Now on to the next assignment. Okay, so now we're on to the homework that was due today. I'm just full of good noises. The first part is drawing a Lewis diagram for PCl3. That's pretty easy. Come on, that shouldn't be much of a challenge to you guys. So you should have something that looks like that. And then it asks, what is the shape of that? When we talk about shape, we're talking about molecular geometry. Whoops, we're missing a pair of electrons in there, so let's throw that in there. Okay, that's the Lewis structure. And because of that non-bonding pair, it is a trigonal pyramidal geometry. Ooh, almost like that one slide. All right, go back to the question. So there's A and B. Part C, now we're told that we have 0.6 moles of PCl3 and 0.7 moles of Cl2 in a 1 liter container. Well, molarity is moles per liter, and since it's 1 liter, 0.6 moles would mean we're going to have a 0.6 molar solution. 0.7 moles means we have a 0.7 molar solution. And at equilibrium, we're told the concentration of PCl5 is 0.5 molar. We want to figure all of this out. So what we need to do is set up our little ice table here and go to work. So let's switch screens. And so we know that we started with 0.6 molar PCl3 and 0.7 molar chlorine. We started with no PCl5, but at equilibrium, we know the PCl5, that's really sloppy, that's 0.040 molar. So that means this went up by 0.04 molars, that means this went down by 0.04 molars, this went down by 0.04 molar. So we have 0.56 molars, 0.66 molars, 0.004 molars. So now I got to make that in my graph. So from 0.7, the chlorine comes down a little bit to 0.66. From 0.6, the PCl3 comes down a little bit to 0.56. And the PCl5 starts at 0 and works its way up to 0.04 like that. All right. Part D, explain how the slopes of the curve at equilibrium can be used to show the rates of the forward reaction and reverse reaction are the same at equilibrium. Well, the rates are based on the slopes. It is correct. And we notice, if I shift screens again, when they're at equilibrium, the slopes are 0. So when the slopes are 0, well, they're equal without any question, okay? And they are, in fact, 0 slopes. And so the rate would be effectively 0 because the reaction effectively stops. Okay. Part E. As a reaction occurs at constant temperature, does the pressure inside the container increase, decrease, or remain the same? Well, I can talk about this a couple different ways. One way is looking back at the ice table. Notice that the overall change is decrease in 0.08 molars and an increase in 0.04. Well, pressure and molarity are proportional. So if the molarity is going down, the pressure is going down. And really, it comes down to moles of gas. We had 2 moles of gas that we're starting with. We're ending with 1 mole of gas. So every time we mix 2 of those reactants, we get 1 of those products, which means we're getting less molecules and thus less pressure. Okay? So the pressure decreases because the number of moles of gas goes from 2 moles to 1 mole based on the reaction. And finally, we get to make pictures. Ooh, flowers. Pretty. So we're told for the reaction that the original equilibrium was the big tall box, and then they changed the volume. Okay, so Chatlier's principle says the system's going to adjust to that. So it adjusts by going to the side that's going to have, since there's less space, we want to, go to the side that needs less space. So we're shifting the reaction to make more products. Okay, and so that means we have to have more of the PCl5. But keep in mind, things still have to be in a certain amount of proportion. Notice if I just talk about the phosphorus in the middle, there are 6 total dark circles in this diagram. So that means in my diagram, I need to have only 6 dark circles. I can't create or destroy matter. And then if I added up all the little white circles, there's 30 of them. I need to make sure that there's still 30 of those. So you got to make sure that you're not losing matter when you do these. Okay? So there was more than one possible answer. One possible answer was this, where we just had 1 extra PCl5. So there were 3 before, now there's 4 of them. And that meant that the number of PCl3s had to go down, and the amount of chlorine had to go down. And I could have extended it out further from there, as long as you worked within the proportions. Okay? So if you have questions, let me know, email it. Now it's time to go watch those AP class videos. Woohoo! See you guys on Friday. Bye.